There it is. Helps if I unmute myself. Good evening, y'all. Welcome back. It's been a while since we've done one of these, huh? Yeah, it's been a busy couple of months. But I was at an estate sale yesterday out in the suburb of Chicago here, and I found this guy. If I can get this to focus. Yeah, look at that. Let me get you a little bit better view of it there. Look at that. So this is an analog dial, right? That's clearly meant to show... Excuse me. Heading, right? We've got 0 to 360 degrees and a calibration scale as well. And this is probably from, so the estate sale was from a ham radio operator who passed away recently. What we in the ham radio community would call a silent key, which I think is a kind of a lovely term. And so I would expect this is probably was an indicator that was indicating like which direction his boom antenna on top of a tower was pointing. Or maybe that was a project that never happened, who knows, but this was in his affairs, and I was like, well, that's freaking cool. I'm gonna do something with that. And then I thought, well, I might as well do this as part of a stream, and just talk a little bit about how to control these beautiful analog panel meters, like the ones arrayed on the desk before me, how we can use them with analog projects, how we can use them with digital projects, how you can hook them up to an Arduino and drive things, and if you find one in the field, how to like make sure that it actually works and is functional for your purposes. The only bit of side business I have tonight is tonight's beverage of choice is a basement party from Temperance Brewing Company here in Chicago, which is a lovely brewery. If you're drinking something tasty out there tonight, and I'm always curious to know, or if that's just water, that's also fine. No pressure. Hydration is a good thing. Oh, yeah. And I remembered to unmute myself this time, which usually doesn't happen, so all is good. So let's just get started, huh? Let's see here. So let's go back to the table and just have a look at the various meters that we have here. So what do we mean when we say an analog panel meter? Well, they come in many different forms. Probably the one you have seen if you have purchased one newish is something like this. Plasticky... God, it's got a lot of plastic in it. So we've got a plastic case. It's got a little movable needle in there. Let's see if I can get this to focus. Yeah, there we go. And this one is labeled for, 0 to 250 volts. And we'll find out later if it's actually measuring 250 volts or something else. This is the first key point, is that the legend, the printed values on this meter don't necessarily correspond to what this physical piece of hardware is going to measure. It's just, we can think of it like the gas gauge in your car, right, has a needle meter probably just like this one. I mean, maybe you have a fancy car that has a digital meter nowadays, but many cars still have a needle meter. And somewhere in the fuel tank, there is a little sensor that's calculating or figuring out how much fuel is left in your tank, probably a float sensor of some kind, turning that into a voltage, and then that voltage is showing up as a thing that's driving your meter, and we'll look at exactly how that works in a little bit. So this could be labeled in gallons or amps or volts. It doesn't necessarily mean that just because you buy a meter labeled 250 volts that it's set up to measure 250 volts without some additional external supporting hardware. So that's one thing to know straight off. They may or they may not, and we'll talk about how that goes in a little bit. There are lots and lots of different styles of panel meters. Let's see if I can get my focus is a little bit wacky today. Come on. Focus. There we go. So this is one that's labeled for 0 to 800 milliamps DC. This says in the corner, I don't know if you can see down here. Let me see if I can get the focus there. Canada. Here, let's focus on my hand. You punk. There we go. Canada patent 1945. This is a Hickok model 56R. And I just love this old metal style of like aeronautic panel meter type of thing. Yeah, really, really juicy. I don't know why my autofocus is freaking out today. Maybe if I just zoom in a little on things, that's a little better. You might also have like this really cheap style of like vertical panel meter here. There we go. So this one, is that right set up for y'all? Yeah, so this one is labeled for plus or minus 5 kilovolts, which is kind of incredible. But this kind of drives home the point, like there's no way we're going to be putting 5 kilovolts directly across this little tiny piece of hardware, right? We would fry things would arc, it would be bad. Like that's a very small gap for 5 millivolts. Almost certainly we would be using some external hardware to translate a voltage measurement into a a measurement that would drive these directly. So again, just because the label says 5 kilovolts doesn't mean you should put 5 kilovolts directly in here. And then we have a few other pretty ones. This one I think was a gift of friend of the channel, Kenneth Finnegan, at some point in time. This is one that is just labeled 0 to 100 with no scale. Oh, here. This one says full scale 500 microamperes. I actually didn't see that before. That's pretty great. So that's going to give us a clue as to how to drive this, that if we put 500 microamps through here, we should see the needle deflect from 0 all the way up to 100. And then, of course, there's this guy, our heading meter. So we can display quantities other than current and voltage with these. Of course, we could display heading, we could display sound level, we could display forward and reflected power, right? If you're a ham radio nerd, you might display, forward and reflected power on some analog needle meters and things like that. So lots of different uses, lots of different styles, but they all work in essentially the same way. Let's figure out which one of these, because this one is biggest and prettiest, in my opinion, and is helpfully labeled for us, let's start with the big Weston meter here. Just going to move a few of these other items out of the way for now. Let's see, let's move this over here. Let's bring that on the floor. Yes, good. Move that out of the way. Move that out of the way. Okay. So let's come back to our Weston meter here. Let me, I'll tell you what. Let me see. You can just look at my phase only while I mess with the camera settings. I'm going to just really quick adjust here and see if I can get my my autofocus playing just a little bit nicer. I think I can. I think I'm going to set it into, if I put it, this is inside baseball. Oh, well, there's 2 meters now. If I put this into video mode, it should be a little bit more aggressive with the autofocus and try and keep it more smooth. Yeah, so that should be all right. Okay, so let's look at this Weston panel meter here. So on the back, we have 2 terminals, which someone at some point in the past labeled, you can still just see the Sharpie there labeled with a plus and a minus, and that's very helpful because for a DC panel meter, polarity does matter. If your meter is unlabeled or potentially bidirectional, you can usually be safe with just putting just a little bit of DC current through it. And if the needle moves in the wrong direction, like if it tries to go, off scale low, you just stop and reverse the direction and move along. But this one is helpfully labeled plus and minus here. So let me show you how. Let's pretend for a moment that we didn't see this 500 microammeters full scale measurement down there. I also don't know for a meter of this age if that's going to be accurate. So let's see how we can determine from first principles how to determine the full scale current reading of a meter like this. And I should say, almost all of these meters, really all of these meters, the mechanism in the center is going to be very similar. It's going to be a very low current ammeter. So it's going to be, in this case, we're putting, 500 microamps through. We'll deflect it all the way to full. Some of them are like 50 microamps. Some of them are as many as like a few hundred milliamps. But that's sort of the range that we're talking about. Now, some of these will have additional internal circuitry to help them measure other quantities like voltage or what have you, or it says a different scale of amperage. So you don't have to always be measuring just 1 milliamp. There's ways to set up that you don't, and we'll talk about those in a little bit. But when we've got just a raw meter like this, or what we think is a raw meter, we can be pretty sure that what we're ultimately going to be displaying directly is a microamp to milliamp range current reading. And this one we secretly know it's 500 milliamps, or it should be. But assuming we didn't know that, here's how we might figure that out. I'm going to take my leads from my benchtop power supply, and I believe I still have this set up for 1 volt. Yeah, there we go, 1 volt there on my little tiny pocket voltmeter. And you could do this with any voltage, right? If you only have a 5-volt power supply coming off of your Arduino or what have you, you can totally use another voltage. I'm just using 1 volt because it's going to make the math very easy for us in a little bit. And because our readings are all in the microamp to milliamp range, what I'm going to do is start with a quite high resistance and then work the resistance down until I find the resistance that makes the meter go to full scale, and then using Ohm's law, voltage equals current times resistance, I can figure out what that maximum current was that made that meter read full scale, right? So let me show you an example. So I have here, just off to the side, I can line them up here a little bit. So I have my resistor bins, right? I have my bin of of 1 ohm resistors. I have my bin of 10 ohm resistors. I have my bin of 100 ohm resistors, and so on. Oh, you know what? I am going to, sorry, I know I'm just messing with camera settings now. You don't need to look at it while I do. But this is so reflective on the table here. It's making me a little bit bonkers. I am going to put the camera into manual mode, and so it stops changing the brightness value every 2 seconds, because I don't know if it'll drive you nuts, but it'll make me a little bit nuts. Okay, that's pretty good. All right, so where were we? We were looking at our resistor boxes. Yeah, so I've got my range of resistors here going from 1 mega ohm is sort of the largest that I pulled out, all the way down to 1 ohm. And I'm actually, as I pulled these out, I realized I'm missing my 1 kilo ohm. I think I've used them all up on a recent project, so that's not going to be a huge deal. It's actually going to let me show off a different technique for determining the full-scale current reading of these meters. But we'll get there in a second. So I'm going to start with my 1 mega ohm resistor. I'm just going to pull one out of the box there. I'm going to hook up the negative lead of my power supply to the meter. It could be either, but we only want to hook up one at this point. And then I'm going to attach a second clip lead to my resistor here. And then when I touch the positive lead here and this resistor, we're basically going to be putting 1 microamp of current through this meter. And this is where using 1 volt from my power supply is really handy, because I know that 1 volt divided by 1 mega ohm is 1 microamp, right? 1 million times 1 millionth equals 1, right? Like I said, you could do this math with any voltage you had that was convenient, but since they have the ability to put out exactly 1 volt, I thought that might be nice, so I'm not trying to talk and do too much math at the same time. So let's see what happens here. You can see that meter movement is just down here. Let's actually, before we start, let's calibrate that movement. Let me grab my screwdriver here, and let's see if this is calibration. It usually is. Let's see. Yeah. So all I'm doing is rotating this little Phillips head screw on the bottom here. Hey, Dave. Good to see you. Yeah, sexy, right? I think this is from Kenneth ages ago. So most panel meters will have often a little Phillips head screw in the front somewhere, and by tweaking that, you're actually adjusting the tension on a couple of the springs inside of this. So I'm going to start by just zeroing out the meter movement to 0 there using just the Phillips head screwdriver. And let's see if we can figure out what the full scale current on this thing is. So I'm going to take my 1 volt in my power supply. I want my 1 mega ohm resistor, and I tap, 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 tap. So if what I want to do, if I connect this here, and it turns out it's way too much current, this thing's going to shoot up and start to heat up, and I don't want to damage anything, right? So I'm just going to tap, 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 tap. I'm not seeing any movement here, which is a good sign. It's what I want to see. And by that, it's not shooting up to full scale and potentially heating up the very fine wires inside of this. So now I will pull out a 100 kilo ohm resistor, going from 1 mega ohm to 100 kilo ohms, and we'll tap, tap, tap. Okay. You can see that there. I'm just getting a little bit of movement. So I know I'm not too far off, but I'm seeing a movement from maybe 0 to the 2 notch on this indicator, which is actually about right, because we secretly know this is 500 microamps, right? So, but again, pretending we didn't know that, let's go up one more order of magnitude. I'm going to grab a 10K resistor here. So if the previous deflection was from 0 to 2, this should be 0 to 20. And we're pretty close. We're at like 19.2 on the meters. That's pretty darn close. So we could do two things here. We could say, well, I'm going to assume that 10 kilo ohms is 20% of the way. So if I had a fifth as much resistance, I'd be at full scale. So I need a 2 kilo ohms of resistance is a full scale reading at 1 volt. Or to work the math the other way, 500 microamps is full scale. Now, as I said earlier, my 1 kilo ohm bin is empty today, which is unfortunate. But what I do have that's going to help me do this is some variable potentiometers. That I also picked these up at the same estate sale where I got the big heading meters. I got these for $1, and they're really beautiful. So for those who may not have seen these before, right? So this is a potentiometer is a variable resistor, usually a contact, a bunch of resistant material, and a wiper in between that moves along a track of resistant material to change the relative resistance of the two sections that you're measuring. A normal, quote-unquote, potentiometer has one turn, or maybe not quite one turn of rotation before it's all the way rotated one way or the other. A multi-turn potentiometer spins multiple times before it gets to one or the other end of its travel. And so it's not necessarily a given that they will all have these fancy dials. In fact, I've got another one here that I just slapped a little knob onto. So this is a multi-turn pot. This one is 200 kiloohms. I just put a little dial on here, but you can see it spins many, many times before I get to the end of its travel there. And similarly, it has 3 terminals on the end, just like our other ones do here. But if you can find them with them or buy these, and you can absolutely buy multi-turn pots, you can absolutely buy these fancy dials, which have a couple of different names. I've seen them labeled as like multi-turn potentiometer dials or vernier dials. I put a couple links in the description of this stream/video. You don't have to go and buy those specific ones. They're just like random ones on Amazon, but they have a bunch of the keywords in the listings for like, how did you Google for that? Oh, right. Some people are calling these one thing or the other. Anyway, they're just an example of what you might find on the internet. So the nice thing about these vernier dials is, so this is a 10-turn potentiometer I happen to know, and I have my dial labeled here with an inner dial and an outer dial. My outer dial measures the percentage along a single rotation, right? 10, 20, 30. And you'll see when I spin this all the way back around to 80, 90, 100, the inner dial has gone all the way to 1. So these are sometimes called a turns counting dial because they allow you to really precisely position the position of a multi-turn potentiometer, which is really nice, especially if you're using these in like a radio context and you're really trying to precisely set the tuning of a device using a rotational method like this. Now you have a really precise control and an indication of where you are on your dial, right? So you know, oh, well, I can tune into Radio Havana, Cuba, usually around 430 on my dial. And that might not correspond to any physical quantity, but it's always going to be the same for you. Anyway, I just thought those were classy, but we're actually going to use them to help us out here. Rather than using our basic resistor, what I'm going to do is set up, I zoom out just a little bit here, set up my variable potentiometer on the table there, and then I'm going to set my potentiometer to at the middle of its range, so about 5, so halfway through its range, and rather than using a regular resistor, I can now use my potentiometer to find what the full scale deflection of this is, and then just measure the resistance across this potentiometer. So if you don't have to worry about having, just exactly the right value of resistor, you can sort of measure it directly. I should also say, so I pulled out my 1K, my 10K, my 100K, whatever. You could absolutely narrow this down further without a fancy variable potentiometer, right? You could pull out, I could be like, oh, it's a little bit less than 1K. Maybe I'll pull out an 820 ohm resistor for the voltage that I have, and so on. But this makes things pretty darn easy. So what I'll do here is I will just, now starting from the middle, just spin the dial until I see the meter start to move, which so far it is not, which is only a little bit alarming. Oh, you know what? Let's make sure my polarity is right. No, polarity is right. Let's try, just because these are second-hand. There we go. Okay. Yeah, there we go. So a little bit of cruft on this contact here is introducing additional resistance, which is confusing things. So I'm just going to turn this dial this way until my meter movement gets to 100. There is something incredibly satisfying about this that I'm not sure comes across on camera. It's like turning a physical dial, a nice smooth buttery dial, and seeing a panel meter move is very, I don't know, it's very, very satisfying, I guess is the words. So there is about 100 on my meter. So now all I'll do is take the clips off of my potentiometer here, and I will grab my multimeter, which I just had, and I said, don't put it away, Jeff, because you're going to need it. And then I put it away. So let me grab this. We'll set this to the ohms setting. Maybe I'll just move this out of the way for a moment here. And this. And we'll just take a quick reading across those two terminals to see what our resistance was. that we were looking for. 1.72 kilo ohms, 1700 ohms, right? So let's do a quick bit of math to find out what our true full-scale current reading is. Let me grab a piece of scratch paper just here from the side. Oh. You might hear my dog in the background. It is storming like wild in Chicago tonight. As my wife said, it is windy AF. So it's possible I will just lose power at some point and the stream will end. And if that happens, it happens. So we had, remember from our Ohm's law, V equals IR. So I had 1 volt in my power supply equals the current we're trying to find times 1700 ohms. So our max scale current is 1 over 1700. And if I do a little off-screen calculator, because I don't love long division on camera, I find that my current full-scale, let's see, one is 5.88 times 10 to the minus 4, or 588, so 1, 2, 3, 4 amps. So, in other words, 588 microamps, which like that lines up pretty well with the labeled value of 500 microamps that were labeled on the actual meter here. Thanks, Dave. I'll let her. She runs by with the dog next time. I'll let her know you say hi. That's pretty good. This also, I guess, illustrates another property of these panel meters that's really good to know, is that the ratings for them, if you buy one that's labeled with a rating or you purchase one that says, it's 1 milliamp full scale, you almost always are going to want to build either into your software or your hardware some way to calibrate that, because there is a fair amount of tolerance flexibility, especially in older meters. Like if I had designed a circuit that said, okay, I'm going to assume that I have a 500 milliamp full scale reading because that's what this says, I'd be kind of out of luck if now it's almost 600 milliamps that I need to give it to get it to full scale after, 80 years or however old this meter is. So that's the gist of it. That's the gist of figuring out how an analog panel meter can be driven, is you want to figure out what the small amount of current is that allows you to drive that meter to full scale. And the easiest way to do it is to apply a voltage and adjust the resistance of the series resistor going into that panel meter. And that lets you figure out what the current is that drives that needle all the way to full. That's all there is to it. So let's do this for a couple more meters, which I think are going to have some weird things about them. And we'll see what happens. So I'm going to set Big Boy here off to the side, put him in a different pile because we're probably not going to see it again. Thank you, Big Boy. Let's pull next. I want to save this guy for a little bit. He's super classy. Let's pull out this guy because I think this is going to be a lie. So you'll recall this is our meter that's labeled minus 5 kilovolts to plus 5 kilovolts. And I just, for how small and crummy this device is, that seems highly unlikely to me. Now, this is an interesting design in that it seems to be, center calibrated. So I imagine if we apply DC current in one direction, we'll see the meter deflect one way, and DC current the other direction will deflect the other way. But I'm not entirely sure. So let's see if we can't figure that out. I am going to just grab a little stand here just so I have something to hold this meter while we work with it. Because it's so wee and it's so cute, and I don't want to be fiddling with it. So what I'll do here before I stand this up is just attach a couple of our clip leads to the bottom, sort of arbitrarily, because let's see if this thing has markings on it. For polarity. I mean, I'm imagining it doesn't. Oh, interesting. So here, I don't know if you can see just there. Wow, that's really faint. There are 2 little embossed stampings here that look like they say plus and minus. Yeah, I've got a plus embossing on this and a minus on that. That's you're never going to see that. I had to get way up close, but plus and minus there. So that'll be, I guess, the orientation that we start with. Just hold that. Actually, let's flip this around so it's right side up, or I'll never hear the end of it. Hey, Neris. So what we're working on is, I have a bunch of analog panel meters here from my collection, and a couple more that I bought just this weekend, and we're just looking at how to tell what the full-scale reading is on these and how we can like use these meters in our analog projects or in our Arduino projects or digital projects or what have you. Just like the various like gotchas and tricks of working with analog panel meters. Just because I think they're really classy, and they're very satisfying to work with. And to be perfectly honest, in some situations, I find them preferable in terms of their behavior to a digital meter, right? So I have as I have mentioned like 17 times today, I'm a ham radio nerd, and I have a couple of different SWR meters that I like to use, and I find the ones that have physical needles are easier to read and respond to in real time, as opposed to the ones with digital readouts. Just because like the movement of the needle is so evocative and so instantly readable, it's really easy to tell what the thing is doing, as opposed to sort of changing numbers on a screen can be a little bit harder to read. Personal opinion, but... So we've got our meter in the stand here. It looks like it's calibrated to just about 0 to start with, which is a good sign. So let's do the same process we did before with our resistors, just to work ourselves down to the proper range, and we'll see if we can figure out what the scale of this meter actually is. So I'm going to hook up my negative lead directly to the meter. So that's just my power supply there for my bench power supply. Again, it's set at 1 volt just arbitrarily because that makes the math a little bit easier, hopefully. And I'm just going to take my 1 mega ohm resistor and tap, 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 tap. And I'm not seeing that meter move at all. All right. So we'll go up an order of magnitude. I'll grab a 100 kilo ohm resistor. 100K. Tap, tap, tap. Ah, okay, a little deflection. Maybe 1 unit, which tells me that possibly 10K will be full scale. If it looks... Yeah, let's try that. I would guess that's about 1/10 of the way. So let's see what happens here if I grab a 10K resistor, and we'll tap, tap. Yeah, okay, so that's it. That's full scale, maybe full scale plus, which is sort of exciting. So let's see here. So similar to before, rather than... let's see, how can I use the tools at my disposal to figure this out? So somewhere between 10K and 100K is full scale. What I'm going to do is use another one of my variable potentiometers. So this one, the ones we were using before, these big old beasts, are a 5K linear potentiometer. This one, this little handheld one, is a 200 kilo ohm variable. So that's going to be more of the proper range for what we're looking at. So I'm just going to, again, set it to the middle of its range. That's going to be about 100K again. And I know this is a 10-turn pot. So if I turn it 1, 2, 3, 4, 5, we're somewhere in the middle of its range, which is quite good. I don't want it to be at the extreme end of its range rate, because then I might have essentially a 0 ohm connection between 2 of my terminals. And I wouldn't want that, because then... I would be like putting a lot of current through this device and possibly damaging it. So let's see here. Yeah, so as I clip my 2 leads on here, I start to see just a little bit of deflection on that meter. I'm going to spin the dial one way and see what happens. See if I can figure out the direction of spinning that causes it to move upward there. Yeah, we're slowly creeping up, creeping up, creeping up. That's a good sign. Now focus on the meter. The dial, we've all seen dials before. I'll take it out a shot. So there's full-scale deflection there. So now I'm using terminals, I guess, 2 and 3 on my variable pot. I'm just going to disconnect those. I'll get my multimeter back out. And we'll just measure the resistance between those 2 points. You're starting to get the idea of this, right? They are low current ammeters, and to determine the maximum current, the current that leads to maximum deflection, we'll just use a known voltage and adjust the resistance until we figure out what that maximum current is. So it looks like 900 kilo ohms or so through 1 volt is the maximum current that we are looking for. So again, doing a little off-camera calculator work. We get that our maximum, our current that leads to maximum deflection on this meter is roughly 110 microamps. So again, I bet this is a 100 microamp meter nominal, but again, the tolerancing on these is a little bit loose and rough. So it's good to have the ability to change your your parameters after install time if you were using this in a project. So now, actually, so let's see. We remember this one, that was 500, that was, nominally 5 kilovolts full scale. Let's reverse our leads here. Make sure I get this right, and see if just reversing the DC voltage gives me that negative scale reading. Alrighty. So here, I'm just going to reuse the same 2 terminals of my variable pot here. Yeah, So there is, I'm just turning the dial again. So there, as I increase this up to the same value as before, we now see we get minus 5 kilovolts on our meter here. So this is an interesting mechanism. So if you were using this to gauge kilovolts in your device, you would need to set up some supporting hardware such that 5 kilovolts in one polarity yielded 100 milliamps of current in this direction, and 500 kilovolts in the reverse direction yielded 100 milliamps in the 110 milliamps, I guess, in the opposite direction. So let's do, actually, we can do that Ohm's lawness off camera as well. And by off camera, I just mean I have a calculator on my computer that I'm using for this purpose. So using Ohm's law, we can say 500 volts or 5,000 volts divided by 110 microamps is about 45 mega ohms. So one way to drive this meter would be to just put it in parallel with your voltage source and put a 45 mega ohm resistor in series with it. And then the assuming you've gotten the polarity right, if one of the sources was at 5 kilovolts greater voltage than the other side, you'd see the meter deflect to 5 kV this way, and the other way you'd see it deflect to 5 kV that way. I would guess that's probably not the way you would set up this circuit, but you could. You probably would use an op amp to do some voltage measurement and maybe have some isolation so that you weren't relying on this crappy little meter and a 45 mega ohm resistor, but you certainly could. So that's our second meter of the night, this goofy little one. This, I should say, this is a good example. So you'll see as I shake this around here, that needle kind of moves. It's pretty loose and free, and that's a really good sign. If you're buying these used, and what you want to do is give them a little bit of a shake and see that needle is not stuck or broken. And another thing you can do, this actually I didn't know, but in doing some research for tonight, W2AEW Alan has a great video on panel meters as well, and he recommends doing what he calls the short and shake test. Let's see if this works. So what I'm going to do is take just a one clip lead and short the terminals of this needle, and we should see it move a lot less. Yeah, so by doing this, we're shorting out the terminals of the coil that would normally be driven by our magnetic field when we put current through it. And by shorting that out, we mean it's a lot harder for current to be, if we generate any current in that coil by moving the meter, we're going to be resisted by the permanent magnet that's in there. So this is a good sign that the coil is still intact, and the shake when we remove it is a good sign that the bearings are still intact. So a little tip if you're shopping for one of these or find one used, because you'll often, almost all of these I have gotten used from estate sales or ham swap meets or what have you. But you can of course buy them new, like this guy. Now, this guy was in box when I pulled him out tonight. I'm pretty sure I got this at a swap meet as well. I just think whoever had it before didn't actually ever use it. But in theory, it's brand new, and it's labeled for 250 volts, which, again, we'll see if it's actually set up to measure voltage or if that's just, what the labels say. But just like before, I'm going to flip this around and look for polarity markings. Yeah, I've got a little tiny minus sign on that one. So what I will do is, again, we'll just figure out how to get this meter working. We'll do minus. I'm going to replace my variable potentiometer. We'll go back to our normal resistors. And again, we'll start up with, we still want to start with the largest resistor and work your way down. So you start with the lowest current and work your way up, if that makes any sense. If you had a bench variable power supply that would do microamps, that would of course be an even easier way to test these. But I don't. Mine will measure down to milliamps, but it's not super reliable. I put a link to it in the description just so you can see. Like I actually really like it as a bench power supply. It's really good for the price, but it's not super duper precise. All right, so 1 mega ohm, no movement on the meter. Let's try 100 kilo ohms, nothing. Let's look at 10 kilo ohms. Nothing. Maybe a tiny little deflection. So at this point, I'm actually, like I say, I'm out of 1K resistors. That one's a lie, I think. Yeah, that one's in the wrong bin. So I'm actually going to jump up 2 orders of magnitude to my 100 ohm bin. And because I was seeing just like the tiniest little deflection on the previous scale, I don't feel bad multiplying the current by 100 to get to this step, basically. So here we go. Oh, interesting. Can you see that? Just the tiniest little deflection there. It's curious. So that's about the same magnitude as when I was using my 100K. Which is curious. We should have 100 times more current going through now than we did before, and we're seeing about the same deflection here. Let's do a 10K resistor or a 10 ohm resistor. Same thing. Aha. Okay. Let's I'll tell you what. Let's go for gold. I'm just gonna give these 2 banana clip leads a tap. We'll just short it across 1 volt, and we're seeing nothing. Yeah. So here's what's going on here. By stepping down by orders of magnitude through our resistors, we should be increasing the current by 10 times each time we step down an order of magnitude in resistance, right? A circuit with a 1 mega ohm resistor is going to have 1/10 the current as when we have a 100K resistor, but that assumes there's not already a series resistance in the circuit, and we can see by applying like 1 volt to this, there must be some internal resistance already built in. This meter is probably already set up as a voltmeter, right? It has been sort of hopefully calibrated to say that when I put certain amount of volts through it, there'll be an internal resistor there, and that will give us the right position on the scale. So what I'm gonna do is actually just hook this up directly to my bench power supply, and maybe I can even do this in a visible way. Let me hook up my little handy desktop voltmeter here. Because I don't, the bench power supply is not going to fit on camera because it's huge and on my shelf here. But I can do this. Yeah. All right. So that's not the clearest display, but you can see we're at 1 volt there. And now if I reach around and turn the voltage up, we should see. Yeah, there we go. So my bench meter will only go up to 30 volts, which is there. But it looks like we're pretty close. So I've got 30 volts across this meter, and we're reading, what are these gradations, 25, 30? Yeah, so 30 volts on that meter there. So this is already set up as a DC voltmeter, which means it has an internal resistor in it that's limiting the current through the meter, such that if you were to put 250 volts across it, you would see whatever the full scale current reading is of this particular mechanism. And it's probably a milliamp or a microamp, but we don't actually need to know because whoever manufactured this meter did that work for us, which is pretty great. All right, we'll set ourselves back down to 1 volt for the next steps, but that's to say, so you can buy these meters preset up. And when I was looking around online earlier, Amazon has a bunch of cheap panel meters now. It's kind of wild. And they're labeled all kinds of different things: voltage, AC voltage, DC voltage, current, view meter labeling, like sound pressure labeling, and on a lot of the listings, it's really hard to tell whether they, like this one, are preset up with a built-in resistor or shunt to allow you to sort of directly hook them up, or whether they're just all the same meter with just different labels on them and you have to provide the circuitry. So if you're going to buy one of them, and you should, because they're, like I say, they're fun devices and they cost like, honestly, new, like $8 now on Amazon. I can't believe it. Or if you're buying them used because they're super sexy and the old ones are great, I would say don't assume that they have the internal supporting circuitry until you've tested them. They might, but they won't always. But this in particular seems to have a built-in series resistor to measure its indicated voltage range right off the bat. So that's cool. Let me put this down in the done pile. And, okay, let's do this guy. So this one says 0 to 800 milliamps direct current. And I'm curious. I suspect this one may also be set up to display that natively. So what I'm going to do, I'm just going to take my voltmeter out of the circuit here, because it's going to be a little bit cumbersome. And let's see if we get polarity. Let's see if we get polarity here. Yeah, I've got a nice big plus sign there. We'll hook up our positive lead. We'll hook up our negative lead. And we'll go back to our resistor testing. So again, I'm using these resistors as a way of controlling current. If you have a means of controlling the current on your desktop, on your workbench that's more fine-grained than this, you should absolutely use it. This is just a really easy way to like really simply figure out what the full-scale current is through these meters. So nothing seen on 1 mega ohm. Let's go down an order of magnitude. We'll go to nothing seen on 100K. Nothing seen on 10K. Let's go up a couple orders of magnitude. Let's go to 100 ohms. So this would be 10 milliamps. Are we seeing anything? Oh, we're seeing a little deflection there. So yeah, so this meter might actually be set up for 800 milliamps DC. Let's go to our 10 ohm resistor. I'll put that in here. And so this should be, so this is 1 volt, you remember, from the power supply, and we're applying a 10 ohm resistor. So this should be 100 milliamps. And that's about what we see on that meter there. That's great. So in theory, if I were to, here, I'll tell you what, let's double these up. So I'll put 2 10 ohm resistors in parallel, right? So I should have half the resistance. So I should have double the current. So now we should see 200 milliamps. There we go. So this really is calibrated as an 800 milliamp meter. That's cool. This is one of my favorite meters, like this metal bezel. It feels a lot like, so I would say I've mentioned before, but it's been a couple months since I've streamed. I work at a science museum here in Chicago, and we have a 727, an actual Boeing 727 stapled to the wall. And this feels a lot like a lot of the cockpit mechanisms that we have. Like, I don't know that this is aeronautical. It could be any kind of heavy machinery, but this aesthetic is just, I just like it so much. All right, let's put you away now too. We'll do our last meter, and then we'll talk about controlling these like with an Arduino and things. Thomas, hi, good to see you. It's been a minute. Hi, I've been slacking on the streams. Life got a little bit hectic, but we're back. Thomas, you're at a great time. This is the meter that I picked up in an estate sale yesterday that inspired this whole thing tonight, just because I just love it so much. So this is a heading meter that I picked up from the estate sale of a recently passed away ham. Oh, Dave, you should have a meter just like this. That's super cool. Dave, did you use it for antenna heading? That's my guess from what this was, because like I say, this was a ham estate sale, a ham radio estate sale. So I'm guessing that's what this person either used it for or would have used it for, because it was just in this condition. Maybe it was for a future project that never happened. So let's check again. Let's check for polarity. Yeah, I've got a nice plus on this tab here. Do plus, and we'll do minus to the other tab. All right. Okay, so there's our meter. Got a lot of glare off the lights this evening, but I hope you'll forgive me because it's worth it. All right, so now we'll do our same testing procedure that we've been doing all night. We'll just our power supply is set up for 1 volt, and we'll just step our way down, starting with 1 mega ohm, and see what happens. So that's 1 microamp of current through the meter, and that meter is not moving at all. Let's try 100K. A little bit of deflection. Maybe, what are these increments here? Do we think they're 5 degrees? Let's see, I've got 90 degrees here. I've got 2 red hash marks. That must be 30 and 60. And I have, 5? Just looking at my camera view here, I've got 1, 2, 3, 4, 5, 6 in between. So each one of these is 5 degrees. So 10 microamps is a 5-degree deflection, it looks like. All right, so this was a, what, 100K? So let's try a 10K. So this should be a 50-degree deflection, I think. Interesting. Not quite. So that's like a 35-degree deflection going up. So we have 10 times much current, but not 10 times the deflection, which is making me think that maybe there's some internal resistance already built into this that's confusing our display here. Let's go up to 100. Interesting. So this previous reading was like 35. This current reading is like not even quite 180. So I'm gonna guess that there is some internal resistance, and this is actually calibrated to be a voltmeter. So I'm gonna go to 10 ohms now. Yeah, and we're spot on at 180. So I think this is probably set up. So basically what I'm saying is if that, like, by decreasing and decreasing our resistance to become ever closer to 0 ohms, or up to what in theory would be an infinite amount of current going through this meter, we're not seeing an infinite amount of deflection, and that means that there's probably some resistance built into this meter such that it's limiting the current internally. So in fact, here I'm going to take this 10 ohm resistor away, and I'm just going to tap my leads together here and just put 1 volt across this meter, and we're seeing 180 degrees deflection. So we'll leave that connection there, and I'm just going to reach over and dial my benchtop meter up until we get to 360 degrees. And that's spot on 2 volts. So this meter is set up as a 2 volt voltmeter that allows us to control its heading by adjusting the voltage across it. Well, that's fun. I think this is going to be the meter that we play with when we hook it up to an Arduino, just because, like, the possibilities for, like, driving this with a digital mechanism are just so classy. So I think we're going to do that. So I am going to, let's clear some things off the bench here. I'm going to zoom you out. You can play along at home. And we'll just move some things off of the bench. Mostly I have these resistor boxes that I know if I get really excited later, I'm just going to send flying. What was this? Oh, okay. Real quick diversion before we move on to Arduino stuff. I did want to talk about this meter. So this, I don't know when I got this, but I think it's new old stock. I think I got it at a swap meet, and I haven't done anything with it, and neither did the person before me, so go figure. I did verify before the stream that this is an AC meter, so putting DC current through it in either direction does nothing. And you can see it's meant to measure US standard outlet voltage, probably to see are you really at 120 volts, are you sagging, are you peaking a little bit here, and so on. This meter movement is almost certainly just a low current DC ammeter, and they will have put a blocking capacitor and a rectifier in here to let it measure AC voltage. I am not going to try and set this up on stream tonight, just because knowing myself and knowing how these streams sometimes go. In fact, that's why I put fire in the header, because I know when I get excited, I get just a little bit sloppy, and getting sloppy with 120 volts AC seems like a bad time. So we're not going to play with that, but just to say, those are AC panel meters are available as well. They function just like DC panel meters, but they'll have a rectifier and a blocking capacitor built in to allow them to directly measure AC voltage, and you could set such a thing up yourself if you wanted to. All right, so there is our meter. Let's get this driven with some digital technology. Let's see here. Actually, one thing I should say is you could certainly control this directly with analog technology. So let me take my potentiometer here again, and I'm going to need another clip lead. So let's see. So I have my positive and my negative here. So what I really want to know is I think 2 is my center contact. Oh, let's use that sexy, let's use our fancy turns counting dial here. Let's get these set up. So what I'm going to do to control the position of this, which is set up as a voltmeter already, so we don't need to add a resistor to it, to control that directly with a potentiometer, all I'm going to do is I'm I'm going to leave my negative lead connected to the negative lead of my power supply. I'm going to connect the positive lead coming off of the meter to the center contact, the wiper contact on my potentiometer. And I am going to connect the positive lead of my power supply to one of the leads, and then I'm also going to connect the negative lead to the negative lead of the power supply. Let me think this through. Did I get the polarities right? It's positive voltage. Yes. So this is, let me think this through. So this is set up as a voltmeter. Ah, I know what I'm doing wrong. So part of what's happening here is, oh no. No, sorry, I had a little brain fart there. That this is set up for, yeah, okay. So part of the challenge here is that this is not going to be at all linear, right? So if we, I'm going to set my power supply back up to 2 volts, which is what we need for a full scale reading on this thing, and I'm going to use my potentiometer to control the voltage that's able to flow to the device, but I suspect that it's not going to really move until I get to the very end of the scale. Yeah, and so then it doesn't really move at all. So this is not a super good method of controlling this. So I just got excited about the possibility of hooking up a dial, a potentiometer directly to the dial, which we can certainly do with an Arduino as well, but doing it directly is not going to be ideal. Ooh, what Thomas says, the 35mm film projector I was working on the other day uses a carbon arc for its light source, and the rectifier has the beefy ammeter on it. Yeah, you see these a lot in old like power supply circuits or film power supplies. There is some of the old DC conversion gear that we work on the museum that powers the coal mine exhibit has some like, you know, meters that big. It's very satisfying and super cool. Let's get an Arduino thing out of the way. And by out of the way, I mean onto the bench. So, let me grab here a couple of pieces from the other table. So, I've got this little Arduino. I forget which variant this is. It's the kind that has a USB header built in, which is a little handy for our purposes. And we will plug that into our device here. And let me open up the Arduino IDE and just verify that this Arduino is indeed working. So I'm gonna open up my Blink example. I'm gonna make sure in my tools menu that it has found this port on COM3. Yes, and I'm going to pick the board. I think this is a Nano. If I'm wrong, it'll yell at me, but I think this is right. Here, and I can zoom in a little bit here too, so we can actually see what's going on. And I'll hit upload, and hopefully we'll get this little. I guess we already have that light blinking. Well, we'll just see if this uploads successfully. Compiling. Still compiling. There we go. Oh, an error occurred in uploading the sketch. I don't know. I hate that. Let's see. What was our error? Not in sync. Why would that be? Do you have a 168p? If not, I have so many more Arduinos in stock. This is just the one that I happened to grab off the top of the pile. But so if this one doesn't work, I have many more. Unknown board. Uploading a sketch video. Well, bummer. Well, that's all right. I have many more in Arduino up here. In my Arduinos. Yes, you have to look at the table while I do this because otherwise you're looking directly at my tummy, and that's not my favorite view of myself. Oh, do you think we should use this one? That's all charred in black. Is that a good sign? Let's see. All right, that should be good. Oh, you know what I actually have? He said, continuing to do things off camera that you can't see. I think. Oh no, maybe I don't. Well, it's all good. Nothing happened. Nothing to see here. I think I have. I have a little Pro Mini that'll do just fine for us this evening. Now, the only question is it a 3.3 volt Pro Mini or a 5 volts? And I'm 92% sure it's 5 volts. It'll work fine either way, but of course the full voltage output will be different, and the clock speed is different between the two. So we are going to have to figure that out. So we will go to, this is a Pro Mini. Thomas, the fire part was when I was going to potentially be testing a 120 volt AC meter on camera, and I pulled the plug on that one. I just decided that was no pun intended. I decided that was maybe a bad idea to try and make that happen. All right, let's upload that. There we go. We'll see if that works this time. What I'll do is there we go, uploaded, and we should have blinking on our little LED down here. On, off. That's just the blink sketch. Oh, yeah, for sure. No, so Tom, you're totally right. So this was an unfortunate thing that happened to a couple of these Arduinos that I was using to experiment with sending I2C commands between them, and I cooked this one's goose. I think I put 12 volts across it, and the voltage regulator, I put 12 volts directly into the 5 volt rail, and I really smoked it up good. So yeah, those are not going to be quite the thing for this evening. But this will be. So this is a 5 volt Arduino, which is a good sign. So to get this working with our panel meter, we need to do a couple of things. First, let me see. So our meter is set. Actually, our meter shouldn't really matter. I'll actually turn my power supply off, and we'll wire our meter directly to our Arduino. And this comes to the part of the evening that I haven't prepared in advance, so we'll see how well things go. But what I will do here is plug the ground side of things into one of the ground pins on my Arduino. And let me pull another bit of wire here. And I'll plug the positive side into something else in just a moment. So what I'm going to do is, first off, I'm going to pick one of my PWM pins on my Arduino, and I happen to know that pin 9 on the Arduinos that make use of the ATmega 32.8 are a good choice for that. I'm also going to, just for the sake of experimentation, I'm going to get my wireless keyboard out, because it'll be a little bit less awkward to type on than trying to do it all cattywampus with the laptop keyboard here. So let's write a little bit of code. So first of all, we'll set up a pin here to be our output. Also, let me know if the size of the text on screen is too big, too small, or just right. It's like I say, it's been a little while since I've tried this. So I'm gonna say const int output pin equals 9. So that'll be the pin that our meter is attached to. In our setup code here, which will run once at the beginning of our project powering up, I'm going to set it to be an output, and then I'm just going to digital write low. We'll just make sure nothing blows up when we put 0 volts through it. Now it's going to make me save before we actually are allowed to upload it, but we'll do that, and we will upload. Oh, I have to give the digital write command a pin as well. So write to output pin low, and we will upload that. And we should see nothing happen here. If all goes well, we should see nothing happen. That's a good sign. Okay, proof positive. So now in our setup function, and again, this is just going to run once at the beginning of our beginning of when we power up our Arduino. We're just going to do an analog write to our output pin. And remember, the analog write function takes a value between 0 and 255, so it's an 8-bit value. And that will produce pulse width modulated signals in the 0 to 5, well, in the 0 to 100% duty cycle of 0 to 5 volts TTL levels. So let's start with just a... Here, we'll make the computer do the math for us, because that's what the computers are good at. If I wanted to do a 50% deflection here, so we'll say 0.5 of the maximum scale value, which remember here is 2 volts. So I'm going to say 255, which would be our full output from the Arduino, times 2 divided by 5. And we'll do half of that. So so that makes sense. So if I were to give an analog write of 255, I would... I'd be essentially saying, hey, put out just 5 volts at this thing, which is more than we want. So I want, say, the full scale on this thing is going to be about 2 volts, or the equivalent of 2 volts. So I'll take 2/5 of my maximum value, and then for this test, I'll take half of that. So we should see the meter go to the middle point here. Hopefully. I guess we'll find out. No dice. Why not? Now is when things get interesting. I'm having a thought here, which is dangerous. But let's do this one thing at a time. So first, let me see here. What I'm thinking is that my Arduino can't actually provide enough current to make this happen, which may just mean this is a bad choice of meter to use. Although there are ways around that. We can solve that in a second here. So we'll just rewrite our code a little bit just to set the output pin high. Whoop, yeah. So at 5 volts, it absolutely swings absolutely high. So maybe if I just plugged it into the wrong pin. That's certainly possible. So let me re-upload my code with this set to low. So we'll turn that pin off before I do any further connecting. And I'll just make sure that I plugged it. I mean, honestly, it's possible I just plugged it into the wrong place. Let's see here. So we want this plugged into digital pin 9. Yeah, all right. So now, and it's also possible that I screwed the math up here. So instead of doing all that fancy math like I was pretending like I could do on the fly, let's just set this to a low value of pulse width modulation. Right, so 10 out of 255, a low little value, and we'll see what happens. Yeah, okay, so we do get some deflection on the meter there. Good. Whew, well, that's what I was hoping would happen. So clearly, I think what that means is I screwed up on that fancy math we were doing last time. So let's do that. So in theory, if 255 is our maximum of 5 volts that we can output from our Arduino, then 2 volts is about 2/5 of that, or about 100. So let's output 100 on our output module here and see what happens. On our analog right here, that is. We should see close to full scale, not totally full scale. So what I'm actually going to do here is I'll say, let's figure out what our full scale is, and we'll work backward from there. So maybe it's 110. Let's upload that. So over in the code here, I just changed my analog write value to 110, and we'll just re-upload that. There are fancier ways we could do this particular process, right? We could like hook a potentiometer up and like have it spit the values back out to us, but doing it manually is actually, for a single meter, is probably going to be faster for us this evening. Thomas says, woo, math. Yeah, I don't have a math minor from a pretty decent college or anything. Years ago. Okay, so 115 gives us about 115 out of 255 is about our full scale value here. So for the sake of the rest of this, I am going to go back to our code and say const int max scale equals 115, and then we can base the rest of our math based on that. So what I'm going to say here is analog write an integer value that is max scale divided by 2. So now when I upload this, hopefully what we'll see is our meter returns to dead center. Now, it's possible that this meter is not entirely linear, so we'll see if it actually goes to center. That's pretty good, though, huh? That's pretty good. That's very good. So now, just to give like a little, a brief example of how we could use this in code, we could say... in our Arduino code here, I could say, for example, set my pin mode up as an output, and then I'll loop over some things like analog write output pin 0, delay 1 second, so delay 1,000 milliseconds, and then we'll do 90, we'll do 180, 270, 360. So we'll do a quarter of the way around. So we'll say output of max of 0.25 times max scale. Yeah, you could totally use the map function here, Thomas. I'm being a little bit manual with this. Oh, we'll do int 0.75 times max scale, and we could do int. I guess int max scale is a little redundant, but just for the sake of illustration. So what this should do is, over the course of 5 seconds, should set the meter to 0 degrees, 90, 180, 270, 360, and then repeat forever. And yeah, there we go. Okay. So yeah, so by changing that pulse width modulation value, essentially how much equivalent voltage is going to our meter, and therefore how much current is going to our meter, we can change the position of that analog panel meter, which was our goal for this evening. And if we had chosen a meter that wasn't already set up as a voltmeter, we could choose the appropriate resistor for this Arduino to drive it directly. In fact, maybe let's do that now. So let me undo this meter. I'm actually going to leave all of the code the same, but we'll just take our small meter off of the bench here, and let's bring back the big boy. Oh. Let's bring back this guy. So we said, we said earlier that this was about 588 microamps full scale on this thing here, right? So just move the Arduino out of the way for a second and grab our Mathemagic sheet. So what we said earlier was we're going to use Ohm's law to figure out what resistor we need to put for 5 volts, because that's what comes out of our Arduino. So we'll say V equals IR, our old friend Ohm's law. So 5 volts equals 0.000588, 500 microamps times R. So our resistor wants to be 5 divided by 0.000588. And as we've established already this evening, my math is not to be trusted, so I'm going to use my handy-dandy off-screen calculator one more time, and I get that I want a resistor of about 850 ohms, more or less, which that's a curious value. So I think I'm going to... I think I have an 8.2 kilo ohm resistor that I should be able to use for that purpose. So let me, again, if you don't mind looking at, this very classy meter for a second, I can reach behind the camera here up into resistor storage to the bin with the 8.2 kilo ohm resistors. And, okay, so got my box O resistor things. Let's see if we can't find 8.2 kilo ohms in here. 470, 8.2K. Great. This was a very satisfying afternoon when I went through and binned all the individual resistor values in the E12 series. And it has paid off ever since. What I don't really have is a great workflow for remembering to buy more of a particular resistor when I've run one out. But what are you going to do? So what I'm going to do now... Duty calls this, Thomas. Thanks for stopping by, Thomas. Good to see you again. I hope to do these a little more frequently and maybe schedule them a little earlier. But we'll catch you around. Thanks, man. So this is going to be how you hook up an arbitrary panel meter to an Arduino for control. So I've determined that if I'm going to want to, make this a 0 volt to 5 volt meter, I need a resistor of about 80 8.5 kilo ohms, 8,500 ohms. So I have an 8,200 ohm resistor here. So I'm going to not want to apply the absolute full 5 volt range here, but that's fine for my purposes. So what I'm going to do is just take my resistor. I'm going to use this breadboard because I have it here. Makes my life a little bit easier. I'm going to hook up the output pin of my Arduino to one side of the resistor, and then I'll hook the input to my meter to the output. So I'm putting the resistor in series with the panel meter, and then I'll just hook up my leads again. My positive lead going through that resistor to the positive lead as indicated on the meter, and the negative lead to ground on the Arduino. Now, I haven't adjusted any code yet, so when I plug my USB cable back in, we're still using 115 out of 255 as our maximum value, so we should still see that 1 second tick, but it's not going to get anywhere near full scale. But just to show you that that works, and I hope it does. And again, making sure things are actually plugged in correctly. Yeah, there we go. 1, 2, 3, 4, 0, 2, 3, 4, 5, and 0. So it actually, so we said that a full 5 volts, a full, a maximum amount of current would be a little bit over full scale because my resistor is a little bit undersized. But luckily, it looks like, just sort of by chance, my current value, which is 115 out of 255 for that PWM, is landing me about 50% of the way up the meter. So I'm just going to double this. I'm going to say my maximum scale value is now 230. We'll upload that. See what happens. Right, now we've uploaded. Yeah, there we go. So now again, we're going 0, 25%, 50%, 75%, and full scale. Maybe a little bit beyond full scale there, actually. So yeah, so that's the gist of controlling an analog panel meter with an Arduino. There's 3 steps. One is figure out what the maximum current, or rather, what the current is that yields a maximum deflection on the meter, using one of the methods we talked about earlier. Then, given that you have a probably 5 volt Arduino or maybe 3.3 volts, figure out the equivalent resistor to create that current coming out of your Arduino, and then use something like the analog output function to create that equivalent create the necessary voltage to put the meter wherever you want it in physical space. And that's it. So I was just looking around sort of behind me at all of the various modules and things, and thinking about what would be another fun demo to do here. I mean, we could easily control this via an Arduino with a potentiometer, but that's not a terribly exciting demo. I was just thinking about if I knew where any of my sensor modules were. I have one here that's a little bit finicky, that I'm a little bit scared to try to figure out live, but we might be able to make it work. So the module in question is this time of flight sensor, the HC-SR04, and I've had a little bit of finicky trouble with them in the past, but I'd be willing to give it another go. Let's see here. Mostly what it's going to mean is me finding a library for this and then demoing it live. But that would be fine. Let's see here. Let's see if we can't make that work. I'm not going to show you my web browser because that feels like a little bit bonus personal. But I should be able to pretty quickly find. Very good. In the library manager there, Arduino. What is that library called? HC-SR04. All right, so we will go into our sensor library here, or into our Arduino IDE. We'll go to our library manager. We're going to manage libraries. And there we go. We'll wait for it to update its list. We'll say HC-SR04 in our library manager here. There we go, and we'll see what pops up. Looking for one, there isn't, let's see if there's one published by the Arduino folks themselves. There's a bunch of these in here. I'm just what is going to be the most, reliable? It's a little bit unclear because they're just alphabetical. What was the one that was referenced on the Arduino forums there? HCSR04. Oh, I was actually able to just click and download it from the Arduino website there, which is a good sign. I'm going to say add zip library, and I'll come over to my downloads folder, and I'm just going to select off camera here my library that I just downloaded, HCSR04, include, and then include library HCSR04. Now let's see if if it comes with any examples. Yes, it sure does. HCSR04. All right, so we'll sort of figure this out live, but I think that'll be fine. Oh, this is really dead simple. Initialize an HCSR04 object with trigger pin and echo pin. And then this one is just bouncing the measured distance out to serial, which I guess we'll leave for now as we get this set up, but ultimately we'll do something a little bit fancier. So what I'm going to do here is, let's just get this set up. So I have VCC, here I can show you this actually on the thing. I have a VCC pin and a ground pin, trigger and echo. So we'll need to get all of those wired up. So, oops, we will unplug the Arduino so we're not wiring live, because that's always a good practice. And figure out, the one thing about using these nanos is it's a little bit cumbersome. It's like the pinout is kind of masked by the components, so it's a little bit hard to see where things are. So I'm constantly having to Google what the actual pinout of them is. Let's see here. Pro Mini pinout. Show me that pinout. Get bigger. Let's see here. Arduino Pro Mini pinout. No. Here we go. VN ground reset. VCC is pin 4. Okay. So I should have 1, 2, 3, 4. Is that pin there? That's VCC. We're just going to do some quick and dirty wiring for the sake of this demo. We could be fancy and clean about this, but I mostly would just like to get this working. Let's see here. Grabbing up a little bit of wire. Snip that. That'll be our ground connection. And what was our ground pin? Ground is pin 2 on this side. And then my other 2 pins are trigger and echo. I can use those. John says, I got a box full of analog meters I bought at a surplus store a while back and I've inspired in particular. Oh, that's great, John. That's awesome. Yeah, there was a full box of panel meters at this estate sale I was at, and I was jonesing for them, and I decided to pass. And if I had planned then that I was going to do this tonight, I should have just kept them. But there is something very appealing about them, right? Like I don't know quite what it is. Maybe they just speak of a more civilized age, but I really do like them. Well, glad. Well, I hope you have success with them. I hope this has been a little bit helpful. I should say I haven't done the YouTuber thing yet, but if you are trying things and you want to share them, I would love to see what y'all are doing. Twitter's probably the easiest way. I'm at Jeffers Glass. It's in the title bar there. But yeah, keep in touch. And if it's like, oh, this is not working like you said it would, Jeff. Now my house is on fire. Well, I'm not liable. Don't sue me. But happy to chat about things. So let's see. So I have according to my Arduino code here, it's just this example that came with the library. I need my trigger pin hooked up to D5. Did I get these backwards? I need my D5 hooked up to my trigger pin. Yes, I did get them backwards. And my echo pin hooked up to D6. Okay, so let's just upload this as written, and we'll see if we can actually get the distances spitting out in serial, and then we'll return to our panel meter demo. Oh, problem uploading to board. Oh, helps if I plug the Arduino in, I suppose. let's see here. Okay, so this is uploading. It's a good sign. And let's open our serial monitor. That's a good sign. Okay, so if I move my hand close, I get a pretty close value, a pretty small value. If I move my hand far, I get a larger value. I don't know what units these are meant to be in. But it looks like, so if I you can't really see me here. If I have my hand about at my face, it's like the value is like 60-ish. If I put it right up close, it's about 2-ish. So those will be maybe our range of measurement for this example. So let's save ourselves a new sketch here. I'm going to get my keyboard back out. And we'll call this something for now. Just so it lets us mess around with it. Okay, so now we're basically going to merge the sketch we had earlier with this one. So I'm going to say const int output pin equals 9, const int max scale equals 230. I'm going to take out my serial measurement here for now, and I'm just going to, in my setup, say pin mode, output pin output. And then in my actual code down here, in my loop code that's going to run over and over again, I'm going to say, instead of outputting the results of this hc.distance function directly to the serial port or the serial monitor, I'm going to do something else with them. I'm going to say analog write to my output pin, and then the value that I want. So my output scale runs from 0 to 230 out of 255 in the units that the analog write function wants to use, yeah? The hc.dist function that we've got here, we know from our experiments a moment ago, is going to give us values in the range that we care about between 2 and about 60, I think is what it was. So what I want is sort of scale the range of results of this hc.dist function from between 2 and 60 to 0 to 235. And as Thomas referenced before he left, the built-in Arduino map function is really useful for this. So I'll say map of this value from the starting range of, let's say 3 to 60, and map that to 0 to 230. And then just for good measure, I'm going to wrap this in an int function so it outputs an integer, just in case that matters. And we'll just do that over and over again until the program stops. And if all has gone well, and it usually doesn't the first time around, we will have a panel meter here that is displaying the distance that my hand is away from the sensor. So let's upload it and see if that works. And like I say, let's not get our hopes too high, because usually it does not work first time. Well, it's uploading first time. That is a better sign than sometimes happens. Let's see here. So kind of works. Kind of works. Interesting. So you know what I'm going to do? So this is cool. So the troubleshooting part of this is also, I think, going to be interesting, right? It's kind of working, but it's also kind of all over the place. What I might try first is just slowing things down a little bit. So let's see here. So I'm going to go back into my code and just put a delay of, say, 333 milliseconds in here. All right, so it's only going to be taking 3 readings a second, or thereabouts. So maybe that'll tell us something about like if individual readings are wrong, if it's just freaking out because it's measuring things too frequently. We'll just sort of get a better sense of it. So if I put my hand here, we'll see the meter is all the way high. Ah, interesting. When I get really close, it gets confused. But that's more like it. So it's not a terribly precise, it's a little bit freaking out there. But as I move my hand further and further away, we do get a general sense of that it is acting as a distance meter. That's so cool. So now, okay, so now that we know that we have basic functionality, let's decrease this delay. This is what I meant when I said earlier that these time-of-flight sensors have been a little troublesome for me in the past. Like, their behavior is not exactly as predictable as I would like. But they seem to be behaving all right this time. Do we upload? We did. Why are you not outputting? Uh-oh. Uh-oh, I've broken things. No, I've broken things. Let's see. Has something come loose, perhaps? That seems most likely. My meter is not attached to anything anymore. If I attach the meter properly, yes, there we go. All right, so now, now if I come back here, I put my hand close, and I'm at close distance. I move my hand away. That's so cool. So the immediate instinct that I'm having here, you can't see my hand all the time, but here if I bring it into frame, the immediate instinct that I'm having is one of the best escape rooms that I ever did, and this was I don't know, 3 or 4 months pre-COVID. It was back when escape rooms were undeniably very fun and acceptable. Was this L car, so a replica of the CTA cars that we have here in Chicago, and it was built by a couple of really nerdy theatrical makers. And the amount of mechanical responsiveness of things that they had built into this escape room was so cool. There is a Morse stop on the CTA red line, and the little LED that would appear on the train line that would show you what stop you're at. And this one, the Morse stop was blinking and Morse code a message at you. There was one of those tilt-a-ball mazes that you had to do to get the next piece of a clue, but it was mounted in the ceiling where you couldn't see it, so you had to do it all by sound, and another puzzle had given you the map to this thing. Anyway, super cool production. All this to say, the analogness of this meter movement is giving me strong vibes of that in a way that I really like. I don't know, there is just something so satisfying about them. Yeah, super. So this is using a time of flight sensor hooked up to an Arduino, and it's just showing me distance in real time on this analog meter. How cool. Neat. Well, I have one more thing I want to talk to y'all about before we wrap it up for the evening, and that is, as I mentioned earlier, this style of plasticky analog meter is really available nowadays, and I did put a couple links to them in the description. Don't buy those specific ones, buy the ones that are right for you, but this style has become wicked cheap, and that's super cool. Now, let's say you have one of these, I have this voltmeter one, that happens to be set up as a voltmeter, but let's say I want the scale to be something different. Or maybe it's even if this was going to go on, say, my 208 volt single phase power that I have in my workshop at work, because we power some lighting circuits from in there, right? It might be nice to hook this up and have it say, oh, well, 208's looking more like 220 today, a little extra power coming out of there. It'd be nice if I could replace the face of this meter with something that was a little bit more representative of what I was actually doing with it. And thankfully, there is software for that. So what I'm going to recommend, and what I've linked to in the description, is a piece of software called Meter, or Meter Basic, from Ton Software. And I will bring it up here. So this is Meter Basic. To me, a little bit confused. It's not the most, not the cleanest piece of software. You can see it's having some issues with my monitor sizing over here. But what it will do, hopefully I can get this to play a little nice, is it's going to make panel meter legends, much like this one. So I'm just going to say, use the design wizard, and it's going to bring up a screen. You know what it's doing? It's bringing it up on my primary monitor and then getting confused because these monitors are different sizes. Let me see if I can make it a little bit happier. What happens if I just make this one that I'm on my quote-unquote primary monitor? So like I said, this is written by a gentleman. This is a hobby piece of work. It's you can pay for the full version, which has more features, but the basic version does a lot of really useful things. And if you're at all fluent in something like Photoshop or Affinity Photo or Pixlr even, you can do a lot of the advanced features on your own. This is just a handy piece of software for that. So you go into the design wizard here. It's going to ask you to input a bunch of questions to tell you about how big your panel is, and then it'll create this design for you. So I'll say my plate width is, I'm going to make up some dimensions because measuring is a little overkill at this point. We'll say it's 80 meters wide by 45 millimeters tall. bottom to bearing. So that's going to be the distance between the bottom of the actual visible, the actual device and the center of the magnetic bearing itself. So right there where it's centered. So let's say, again, making this up, we'll say that's 10 millimeters in our case. Bottom to mounting, right? So almost all of these meters have a couple of little mounting screws here, and those also are sometimes, though not always, what holds the legend in place. So in this case, we're actually going to reference not these big external screws, but the two small screws there that are holding the legend in place. So we'd measure from the bottom of the plate to those. So we'll say that that's, I don't know, 3 millimeters for our example. Mounting hole separation, so the spacing between those two mounting holes, and again, I'll just make up a dimension. We'll say 25. Pointer deflection, so you could measure the angle difference between the different points on this. That's probably 85 degrees or so. And you could get a protractor out and do this properly, but for the sake of just showing you what this software can do, I'll say 85 millimeters. Actual and virtual offset. Okay, so this is worth looking up in the manual just to double check that I'm correct, but this essentially refers to the difference between where the center of the circle of this meter arc is versus the actual center of rotation. So like if you see in their example here, the virtual center, right, where these lines converge would be on here, but the actual center of the bearing would be down here. This one, they're almost equivalent on this particular meter. They're almost concentric. So I'll say maybe that's 5 millimeters for my example. Major tick length. Now this is just some choices we get to make about design. Let's say I want a 5 millimeter major tick and a 2 millimeter minor tick. And I want a 3 millimeter wide major tick and a 2 millimeter wide minor tick and a 2 millimeter wide arc, and bottom to scale ceiling. Oh yeah, so the bottom of my legend here to the actual top of the scale. I'm gonna have to make up some consistent values here, I guess. If I said the height was 45 meters, let's say that that's 25. Font size for tick marks. Suggested value it says up here is 8. Sure. Label to arc spacing, suggested value is 6. Sure. Bottom to top, let's say it's 30. Number of tick marks is 5. Okay. Major tick marks every how many? 5. It's a lot of choices. The full scale value in units has been temporarily set to be the name as the number of tick marks. You may change this later, it says. You now have a simple scale, which can be added onto and edited in the main part. So let's, now that we've done the design wizard and gone through all this, let's see our completed design. So this is the design that we've created with our little, our fake values there. But you can see I can adjust all of them, right, by adjusting these values on the left. So I can adjust my title placement, it does nice things like when I adjust my meter placement, right, it scales it up and down appropriately. So I can really mess with the aesthetics of this, including if I've gotten any of the measurements wrong, like my virtual spacing, my arc spacing. Maybe I want the labels to be bigger. My major arcs are bigger. Maybe I want, I don't think I can adjust number of ticks in this screen. How often major ticks, how often tick labels. Yeah, I can adjust where the labels go, except in preview. Yeah, so now that I'm into sort of the main interface, I've gone through the whole wizard. I can go in here and I can go into my scales. And in my first scale, I can increase, say, the number of ticks to maybe include that many. Maybe I want to move my title up. So I can do all this. I can do all of this editing. And the difference between the meter program, which is this, and the meter basic program. The meter basic program, you pay a fee. I think it's like $50, but you get like 10 scales on the things, and you can have lots of discrete text options. I think you can embed graphics on the basic version, but you can like highlight ranges. So if you wanted to be really clear, like this is the green range and this is the red range, and don't go up there, you can do all of that built into the program. For myself, I probably would just use this to maybe like make some initial meters and then go into a photo editing program to like do all that kind of formatting work. But there is there is nothing, this is a very handy program. If you're doing a lot of these, you really could, this would be a really easy way to make a lot of panel meters very quickly. I'm also adjusting here this linearity component, which allows you to make non-linear scales. So for example, if I wanted to have a meter that responded to the square law, let's say I was displaying power using a voltmeter, right, where power is sort of proportional to voltage squared, I might need a meter that doesn't actually represent values linearly, and this program, Meter, will do that for you. So in any case, go explore. If you're playing with these things, John, if you're getting out your meters and want to like label them different things, check it out. Ton software, it's in the description. Just a super cool and handy thing. I tried for a while making my own, like doing the math and laying this out by hand, and I learned a lot, and it was a pain. So I recommend at least starting with this program, and then you can export it to a PDF or an image file, and then just go from there. It seems to be the best way to do things. Oh, I've got 2 sets of meters here. That's exciting. Yeah. Why do I have 2 sets of meters? I must have changed something. Well, in any case, I'm delighted that we got to like our final demo of the evening. I just find this so satisfying. Like when I move the hand up and down, the meter moves along with me. I think this is where I'm going to leave you for the evening, because I'm just going to be here playing with my fun meter movement all evening. Thank you, as always, for joining me on these streams. I know it's been a little while for some of the regulars. Thomas, Dave, good to see you again. New faces, always fun to see. Like, subscribe, all that YouTuber stuff. If you want to hey, I did this cool thing, or hey, I broke my thing and I don't know why, Twitter, like I say, easiest way to find me, at Jeffers Glass. You can also try calling the number on the screen there, 815-OH-MALORT, which is a Chicago liqueur. It's a long joke. That, when it's working, rings the bat phone. I'm happy to take calls in the workshop. I find it this is starting to make a lot of sense to me, because just like I enjoy the sort of like charming analogness of these panel meters, I also just enjoy the phenomenon that we don't have much these days of just getting a phone call and not knowing who it is, but being pretty sure it's a nerd, right? If someone's going to call the bat phone in my workshop, it's a pretty good sign. Like I say, I think it is powered down because I've been reconfiguring the workshop. But I'll get a voicemail if you leave it, either way. Yeah, John, thanks for joining. This is super fun. I was doing like regular Sunday night streams for a long time, and I fell off in the past couple of months as life got busy again. But I hope to do more. I hope this was helpful for whatever you're doing with it. In any case, stay safe out there, stay hydrated, wash your hands, and yeah, I think that's where we're going to call it. Have a wonderful night, and I will catch you next time. Thanks, everybody.